Hi, everybody. It's my pleasure to introduce Oinam Meitei for this talk, who is going to speak about an interesting flavor of VQE. So, Oinam, whenever you want.
Hello, everyone. First of all, thanks to the organizers for putting up this workshop and the opportunity to present our work here. Today, I'm going to talk about a new variational quantum algorithm for fast molecular simulations, which do not use quantum gates and circuits for state preparation, but take advantage of quantum optimal control. Okay, sorry. But first, let's ask this question: why do we want to simulate molecules on a quantum computer rather than the well-established classical computational resources that we have? So molecular simulations on a classical computers amount to computing large vectors of coefficients for the many quantum states for the molecule and store it in memory. Now, this scales almost exponentially with molecular system size. And even for a reasonably sized molecule, the computational resources required to simulate molecule on classical computer just runs out even with the state-of-the-art computational facilities that we have. The picture is different when it comes to quantum computer. Quantum systems themselves, the quantum state of the qubit device is another state vector in the Hilbert space of equivalent dimensions to the molecular problem. Now, we can have a one-to-one mapping between the two quantum states, one containing our electronic molecular wave function and the other quantum state accessible to the qubit device. So molecular simulations on a quantum computer amounts to preparing the quantum state corresponding to the molecular electronic wave function and measuring the observables like molecular energy or dipole moment. Now in the current state-of-the-art quantum device or near-term quantum computers with subsystem noise and short coherence time, one algorithm stands out for molecular simulations, the variational quantum eigensolver. This provides an efficient procedure to map the two states, one containing our molecular wave function and the quantum state of the qubit device. So this is a hybrid quantum classical algorithm, which uses a quantum device for state preparation using parameterized quantum circuit, which contains logical gates. Now, because of the infidelity of the gates and short coherence time of the qubit devices, the number of gates that can be implemented are rather limited. But let's take a look at the VQE algorithm, although this has come up more than once during this workshop. Once we have our molecular Hamiltonian in the qubit representation, we can choose an ansatz for our molecular problem, define a parameterized quantum circuit, and using this parameterized quantum circuit, we prepare a trial quantum state on the qubit device, measure the expectation value of the molecular Hamiltonian, and then using a classical nonlinear optimization, we can optimize over the circuit parameters, update the circuit parameters for the state preparation, prepare the trial quantum state on the qubit device, and repeat until the molecular energy is sufficiently converged. Now let's take a more closer look into how we realize a quantum state on a qubit device. At the lowest hardware level, the quantum computers are controlled by analog control pulses. This means that the high-level quantum algorithms has to be decomposed and compiled down to the low-level control analog pulses. This is actually simple and rather fast. So the quantum circuit comprises of sequence of quantum gates. Now each gate has a corresponding analog control pulses. We can just concatenate these pulses corresponding to its gate and form a set of analog control pulses and execute it on the quantum device. Now this happens almost instantaneously and amounts to just using a lookup table that maps the quantum gate in the circuit to the corresponding analog control pulses and then concatenating it. However, the pulses corresponds to its gate and are not global for the entire circuit. Now, the pulses heavily depend on the number of gates there are in the circuit, which means that the pulse duration can be unnecessarily long because there can be an optimal pulse global for the entire circuit, which is much shorter than the ones that we form out of concatenation. As an example, let's take a look at the gate duration for a 2-qubit CNOT gate. The data here are taken from an IBM Q device. So the 2-qubit CNOT gate, which is often used for molecular simulations in the UCCSD ansatz, is about 500 nanoseconds. Now, if we have more than one 2-qubit gate, it can easily be longer than 1000 nanoseconds. There are algorithms, of course, which aims to optimize controlled pulses for the entire circuit, like the GRAPE algorithm, for example, but they have long compilation latencies. Alternately, we can take advantage of an already established quantum optimal control, which aims to design optimal control pulses to drive a quantum state to a control target state. So we can find an optimal pulse that drives our qubit system from an initial state to the target state. By defining a control objective function, we can minimize over the control pulse parameters to arrive at our target quantum state. As an illustration, the figure on the right shows how this is done. So if we define the objective function as the overlap between our wave functions, initializing using an initial guess for the optimal pulse and performing optimizations, improving the overlap at each and every optimization step, finally coming to an optimal pulse, we drive our system to a state which has the maximum overlap. The dynamic is given by the time-dependent Schrodinger equation. The Hamiltonian has this form, which have this static part, also known as the drift Hamiltonian, and a control part. The solution is a unitary that acts on the initial state to come to our target state. Now, we can include the quantum optimal control in the framework of the variational quantum algorithm by defining the objective function as the expectation value of the molecular Hamiltonian. We can introduce an optimal control routine in VQE to variationally design pulse shapes to drive our qubit to our target state for the state preparation, rather than using quantum circuits and gates. This family of methods we refer to as control VQE. The main idea here is to work at the lowest hardware level and find optimal pulses for our molecular simulations to drive the quantum state corresponding to the initial Hartree-Fock state to the exact full CI state. Now let's look at our control VQE algorithm. So once we have our molecular Hamiltonian in the qubit representation as a linear sum of Pauli spin operators using some transformation techniques like Jordan-Wigner or parity mapping, for example, we define a pulse shape. Now, the pulse shape need not necessarily be fixed throughout the optimizations, but in the numerical demonstration that follows in the later slides, we have fixed the pulse shapes throughout the optimization. We initialize pulse parameters. So using random numbers here just works for most of the cases. And then we use this analog control pulses to drive our qubit to the target state for the state preparation. So we prepare a trial quantum state on the qubit device and measure the expectation value of our molecular Hamiltonian. This is the objective function. And then we use a classical nonlinear optimization routine to optimize over the pulse parameters, update the pulse shape for the state preparation, prepare the trial quantum state, and then repeat until the molecular energy is sufficiently converged. So the difference here to the standard VQE algorithm is that we are not using quantum circuits and gates. So we are working at the lowest hardware level using an optimal pulse to drive our qubit rather than realizing the quantum state using quantum circuits and gates. We have used a well-established transmon Hamiltonian to simulate the qubit device. The drift Hamiltonian has this form. In principle, this supports an infinite number of states, but we had choose to use 3 levels because that's more than sufficient for our test, for our numerical demonstrations. The control Hamiltonian has this form. We also introduce a frequency modulation term of this form on each of the qubit. Moving to the interaction frame, we come to the final time evolution ansatz for control-VQE. Using control-VQE, we compute the molecular energy along the bond dissociation of 2 diatomic molecules, hydrogen molecule and the helium hydride for numerical demonstration. The 2 diatomic molecules has contrasting behavior upon bond dissociation. For hydrogen molecule, the static correlation starts to dominate upon bond dissociation. For helium hydride, there is no correlation at far bond distances. We've also reduced this to 2-qubit problem for computational efficiency in the simulation. We also compute ground state of lithium hydride. Here we have reduced this to 4-qubit problem. For demonstration purpose, we have used very simple pulse shapes. These are square pulses with time segments. So for the 2-qubit cases in the hydrogen molecule and helium hydride, we have used 2 time segments. So one amplitude and an amplitude on one time window and a different one on the other time window. But in principle, control-VQE is not limited by the shape of the pulse or the type of the pulse that we use. In principle, it would work with any kind of pulse shapes that can be experimentally realized. And here for the 4-qubit problem for lithium hydride, we have used 5 time window square pulses. If we look into the dissociation curve of hydrogen molecule, we see that control-VQE and FCI, the full CI, are indistinguishable, almost reproducing the FCI dissociation curve with a maximum error of only 30 microhartrees, and we have an average error of about 2 microhartrees. In this case, we see that the Hartree-Fock state deviates from the exact state as the bond dissociates, in contrast to helium hydride ion, where the Hartree-Fock state becomes degenerate with the exact state as the bond dissociates. Here again, control-VQE and the exact full CI states are indistinguishable. This shows the accuracy of control-VQE. Now, let's take a look at the pulse duration along the bond dissociation of the 2 diatomic molecules. The plot here shows that the optimal pulse that we obtain from control-VQE reflects the contrasting behavior upon bond dissociation for the 2 diatomic molecules. For hydrogen molecule, the total pulse duration increases upon bond dissociation in contrast to helium hydride, where it decreases. Now, if we were to use a quantum circuit comprising of gates for this simulation, we ought to use costly 2-qubit gates here as well, here at this far off bond distances for helium hydride ion, where the initial state is already degenerate with our target state, but control-VQE accounts for this. This shows that the optimal pulses that we find from control-VQE reflects the effect of electron correlation. Now, the optimal pulses that we find are optimal for a given pulse duration. So the total pulse duration enters into optimization as a hyperparameter. This means that we can find optimal pulses at varying total pulse duration. Here we show a plot. Here we show plots. So here we show plots with energy difference to the exact full CI state along the time evolution for different pulses, different optimal pulses with varying total pulse duration. And on the right, we have leakage to higher state along the time evolution for this optimal pulses with varying pulse duration. From the figure from the plot on the left, we see that the time evolution is not a monotonic decrease from the initial to the final state, but involves this decrease, and these oscillations along the time evolution. And from the figure on the right, we see that not all of the pulses, which minimizes the molecular energy are desirable. Some of them have high liquids, like this one over here. There's no obvious trend. There's no obvious trend relating to the liquids, relating the liquids to the duration of the pulses. Now we have also computed the hydrogen molecule dissociation curve with Gaussian pulses. This is so that it also works with a different kind of pulse other than the square pulses that we have considered before. Here we use sum of two Gaussian pulses for now we can see that the square pulses and Gaussian pulses performs almost similarly, reproducing almost exactly the Fulci curve over here. Now let's look into the ground state of lithium hydride. We obtain chemical accuracy for this, which is less than a kcal per mole, with a pulse duration of about 15 nanoseconds. Now, the accuracy that we find for the ground state of lithium hydride is lower than the ones we found for hydrogen molecule and helium hydride. This is likely because of the restrictions that we place on the pulse shape, because if we reduce to less than 5 time segments, square pulses, there's large errors in the molecular energy. Because we simulate the time evolution, we are kind of limited with the computational, we are kind of limited because of the computational cost as it increases. But we are currently working on using analytical gradients so that we can simulate more than 5 time segments or try out with more complex pulse shapes. Now, let's make a comparison between the pulse duration that we find with ctrl-VQE and that to standard gate-based ansatz. The pulse duration here are taken from a mock qubit device available in the QCxQC software. So for this, we consider the RY ansatz and the UCC as the ansatz, and we can see that the pulse durations are significantly different as compared to the ones that we find with ctrl-VQE. So this means that the short pulse durations that we find, we can minimize the loss due to decoherence and dephasing. Now, we can construct quantum circuits corresponding to the state vectors that we find from ctrl-VQE. This we can do it in 3 ways. First, we can use the cat decomposition to construct a circuit corresponding to the state vectors from the unitary. We can also construct an arbitrary circuit corresponding to the state vector, and we can transpile it we did this using the facilities in QCxQC software. And again, using this mock qubit device available in QCxQC, we can obtain the pulse durations corresponding to the circuits. And we see that the pulse durations are significantly longer than the ones that we find from ctrl-VQE. Also, we can see that all of these circuits results in the same state vector that we also get from ctrl-VQE, but with a much shorter pulse duration. Control-Q is an open source code for running ctrl-VQE, highly efficient, and it's user-friendly. It's available online on GitHub if anyone wants to try this out. Now, to summarize, we have a low-level quantum variational algorithm for fast molecular simulations, which uses a device-level control pulses for the state preparation, replacing the quantum gates used for state preparation in the standard VQE with an optimal control routine. Now we achieve significant pulse speedups in the state preparation as compared to the gate-based ansatz. Also, the short pulses that we find from ctrl-VQE means that we can minimize loss due to decoherence and dephasing. Ctrl-VQE also captures the effect of electron correlation as reflected in the pulse duration. We're currently working on using analytical gradients for the pulse for faster numerical simulations. We're going to try out more complex pulse shapes other than the square pulses we have demonstrated here without any increase in computational cost. And we also plan an experimental implementation of ctrl-VQE. With that, I'd like to acknowledge our team at Virginia Tech and at NIST Boulders, financial support from the DOE, and thank you for your attention.
Well, thanks a lot, Oinam, for a fascinating talk. Very interesting indeed. I'm going now to the Slack channel to see whether people are asking any questions. Yeah, we have a couple of them already. So from Nathan Fitzpatrick, basically he's mind blown. Can you go into more detail about the pulse shape optimization process? What is the cost function?
The objective function here is just the expectation value for molecular energy, which is objective function. The expectation value for molecular Hamiltonian, which is the molecular electronic energy. So we are minimizing the molecular energy. I hope that answers the question.
I think so. Peter is asking, what are the limitations of your approach?
If I think of it, at the moment, since we are just numerically simulating it, we have this computational cost with increase in the number of qubits and also the pulse parameters. But this we can easily get rid of when we have this analytical gradient working. With analytical gradient, it would just be the same as computing the molecular energy in one step. Other than that, there should be some limitations, but I cannot think of it.
Okay, question from Bruno's engine. So for gate-based VQE, one can define physically motivated ansatz to work on a specific sector, like singlet states only as shown in other talks. Is it possible to design such ansatz using ctrl-VQE?
Can you please repeat that question?
Yes, I can do it. For gate-based VQE, one can define physically motivated ansatz to work on a specific sector, a symmetry sector, basically, like singlet states only as shown in other talks. Is it possible to design an ansatz with these characteristics using ctrl-VQE?
So we are optimizing pulse shapes at the hardware level. So the circuits, the physical circuits, also translates to control pulses at the lowest level. Now we are optimizing that. So if we define our objective function as to arrive at the target physical state, like the singlet state, for example, then yeah, we should be able to optimize pulses for that.
Okay. Nathan Fitzpatrick is elaborating on his question. So how do you optimize the pulse themselves? What is the variable that you are changing?
Okay, I can go back here. For example, in this 2 time segment square pulses, the only variable that we are changing is the amplitude in this, and the amplitude in this time segment, and also the frequency modulation term, that we have. So it's just 3 parameters on each qubit. And for the 5 time segments, where 5 time segments here, we would be optimizing the amplitude at each of the time window. So we have 5 of them, and then the frequency terms.
Okay. Hans Chan is asking, how did you reduce the number of qubits needed for your simulation?
Okay. So for the hydrogen molecule, for the 2 diatomic molecules, hydrogen molecule and the helium hydride, we use this parity mapping to remove 2 qubits. And for lithium hydride, so with 1 frozen core, we have 10 qubit problem. Then we choose MOs with 2s and 2 pz characteristics for lithium and 1s characteristics for the hydrogen molecule. And then further using parity mapping to remove 2 more qubits. So we reduce that down to 4.
Okay, let's see. I'm going to ask a question myself. It might be a bit silly question, but the examples you have shown are on models for superconducting architectures. I guess this is also applicable to ion trap machines, isn't it?
Yes.
Is there any modifications you have to do for the algorithm?
I cannot think of any modifications that we would have to do. Perhaps if we are simulating, then we might have to change the Hamiltonian that we used for the numerical simulations, but on an experimental implementation scale, I think we do not need to modify anything at all.
The other question I have is related to noise. How do you think the addition of noise will influence the optimization process in ctrl-VQE?
We have tried that, introducing noises for this hydrogen molecule dissociation. Now we find that until and unless the noise that we introduce are of similar scale to the pulse parameters, there isn't any effect on there isn't significant effect on the optimization at all. Now, so for example, if we introduce noise, so this is in megahertz, 2 pi megahertz, the amplitude. So if we introduce something like 100, about the scale of 100 megahertz noise, then there is some significant effect. But other than that, if the noise is much smaller scale, we find that there isn't any effect.
Okay, thanks. There was someone writing something, but it seems that it's not appearing. I think I'll wait a couple more minutes, or 1 or 2 more minutes, to see if anyone comes up with another question. Someone is writing something. Not really. Hans Chan is asking if you have any ideas regarding the scaling of this method.
For an experimental implementation, there shouldn't be much significant scaling at all, right? As long as we are able to run on 4 qubits or like 6 qubits, there shouldn't be much scaling. For numerical simulations, of course, at the current stage, we have scaling because of if you, like for example, if we try to simulate these 4 qubits and we have like 5 or 6 time-segment square pulses, we have many parameters to optimize over, and we are using numerical gradients for this purpose at the moment. So that is a little bit problematic. I mean, the computational cost increases. So other than that, but with the, like I said, like with the analytical gradient implementation, this scaling should go down significantly. It should go down significantly, and so we should be able to try out more complicated pulse shapes and more qubits in the future.
Interesting. I think we have time for one question. Nathan Fitzpatrick is asking, for lithium hydride, do you have a comparison on how much shorter the circuit is than the gate-based approach? How do you expect this to scale for layer systems?
I think we have this in one of the tables here. So for the gate-based ansatz, there's significant differences, but I cannot really say for how it would scale for the pulse duration. So for this lithium hydride simulation, we have used this 5 time-segment square pulses and find about 15 nanoseconds. But maybe if we include more variational parameters to optimize over, maybe this pulse duration decreases down. But I cannot really say anything about that at the moment. But for the standard gate-based ansatz, the compilation time just increases.
Okay, I think it's time now. I invite you to continue answering questions in the Slack channel because people
Right.
are very interested. And thanks again for this very interesting talk.
Thank you.